Welcome back to the Real Number System. Today, in section 2.3, we will continue our discussion of sets. We'll talk about sets operations, we'll continue to talk about Venn diagrams, and we'll also talk about Cartesian products. So let's get started. The intersection of two sets is written as A intersect B. It looks like an upside down U. This is the set of all elements that are common to both A and B. So you'll notice in our set builder notation, we have X such that X is an element of A and X is an element of B. Remember that our AND tells us to look for what's in both or what's in common between the two sets. For our Venn diagram for A intersect B, we begin with our rectangle for our universe. Then we draw our loop for A. Next, draw your loop for B, and notice that the loop for B overlaps the loop for A. Because we're looking for what's in common in both, we shade where the two sets, the two loops, overlap. If A and B have no elements in common, then they are called disjoint sets. Our Venn diagram, we begin with a rectangle. Draw your loop A, but this time, because the sets are disjoint, they have no elements in common, our loops do not overlap. In our next example, we're going to find A intersect B for each of our sets. Remember, the intersect means that we want to look for what's in both or what they have in common. As I look at these two sets, I notice that they both have a 3 and they both have a 4. So A intersect B would be the elements 3, 4. In part B, I notice that set A are our even numbers and set B are the odd numbers. We're asked to find A intersect B. As I look at these two sets, I want to know where the two sets overlap, what they have in common, or what's in both. There's no element that's in both sets, and so A intersect B is the empty set. In part C, once again, we're asked to find A intersect B. So I want to know what elements are in both of these sets. Well, they both have a 2 and a 4. That means they'd also have a 6 and an 8 and ... Well, notice that where these two sets overlap, it's actually set A. So A intersect B is set A for this example. The union of two sets is written A union B. This is the set of all elements that could be in A or might be in B, or maybe it's in both of these. To draw our Venn diagram, we begin once again with our rectangle for our universe. We draw our loops A and B. The union is any element in set A or B or both. Notice that I shade the set A, I shade the set B, and I also shade where the two overlap. Our next problem asks us to find A union B. So I'm looking for anything in A or in B, or maybe it's in both. So A union B here, I begin writing the elements of A, 1, 2, 3, and 4. Then I'll continue with the elements in B. I've already listed 3 and 4, so I don't want to list them again. Then I have 5 and 6. For part B, as I look at these sets and I'm trying to find A union B, sometimes read A or B, I begin looking at the numbers. Well, A is the even numbers and B is the odd numbers. Now when I mash these two sets together, I can count from 0, 1, 2, 3, 4, and ... Think about the union as mashing two sets together to make a bigger set. Finally, in C, when we find A union B, I'm looking for the elements that are in A or B or both. Well, I have 1, I have 2, I have 3, I have 4, I have ... That list continues. I notice that this happens to be the same thing as set B. The next topic we have is called the set difference. So suppose we have a set of students who take art classes, that's set A, and B is a set of students who take biology classes, that's set B. And I'm thinking about my students who take biology but not art. So this would be the complement of A relative to set B, or what we refer to as the set difference. The complement of A relative to B is written B with a minus sign in A. Now never read that as B minus A. This is the set of all elements that are in B, but not in A. In our set builder notation, we have X such that X is an element of B, or X is in B, but X is not in A. Again, the set difference should never be read as B minus A. Minus is an operation on numbers, but set difference is an operation on sets. Let's look at the Venn diagrams for the set difference of B and A, and then also for that other notation we have out there that we'll talk about it. Well, the set difference of B and A is all the elements that are in B but not in A. Now the second piece is the same thing. It's B and not A. It just looks different, but it's the same thing. So here's our Venn diagram. Notice that B is shaded, all of B, except for where B overlaps A. So once again, this is the set of all elements that are in B and not in A. That is our set difference of B and A. Our next example asks us to find several set differences. First, we have the set difference for B and A. Well, this is all of the elements that are in B, but not in A. So as I look at my elements in B, I notice that A is in B, but not in A. B is in set B, but not in set A. And C is in set B, but not in set A. The other elements of B are also in set A, so I do not list them in the set difference. The next part asks us to find the set difference of B and C. This would be all of the elements that are in B, but are not in C. As I begin looking at set B, I notice that D is not in C, E is not in C, and finally F is not in C. Our last part is C minus B. So this is all of the elements that are in C, but not in B. Well, as I look at set C and I compare it to set B, I notice that every element in C is also an element of B. The set difference of C and B is the empty set. There are no elements in C that are not in B. Now we can use Venn diagrams as a problem-solving tool. So let's suppose that M is the set of all students taking mathematics, and E is the set of all students taking English. Let's look at this Venn diagram and describe each of the parts. Let's start with region A. Well, region A is in the M, but it doesn't cover where M and E overlap. So this would be the elements that are in M, but not in E. This is our set difference of M and E. Region B is where the two loops overlap. So this would be the elements that are in both M and E. This is M intersect E. Region C is the elements of E, but notice it doesn't include where E and M overlap. So these are the elements in E, but not in M. This is our set difference of E and M. Region D is our last region. It's outside the loops and it's in the universe. So this would be the elements in the universe, but not in M or not in E. There are ways you can write this with our set operations. For part D, that is not something I expect you to do. In our next example, we're going to put the pieces of a puzzle together. We have 110 college freshmen, and we have some information about these college freshmen. Some have taken physics, some have taken biology, some have taken mathematics, and some have taken a combination of these. What we want to know is how many students did not take any of the 3 subjects. I began by drawing my rectangle for my universe. I have 3 subjects, physics, biology, and math. So I'll draw 1 loop for each subject. Here's the physics loop, then I draw the biology loop, and finally the math loop. Now notice my loops overlap. I'm going to start in the center. 5 students took all 3 subjects, and so I put the 5 where all 3 loops overlap. Now typically with the list, most of the time the way that you see the information listed, you'll start at the bottom and go to the top. So I start with the bottom, in this case all 3 subjects. Then I'm going to look at 2 subjects at a time, and then I'll look at 1 subject. And that's the general pattern that you'll follow with these. Start with all 3, then look at 2, and then look at 1. So there were 6 students who took physics and biology. Now notice where physics and biology overlap, I already have a 5 there. So I subtract the 5, which gives me 1. That means for the top of the I shape, where physics and biology overlap, I write the 1. So these are students who took physics and biology, but not math, and there was only 1. My next piece of information is 8 students took biology and mathematics. So I look at where my biology and mathematics loops overlap. There's already 5 in that overlap. 8 minus the 5 from the overlap gives me 3. And I put the 3 in the right-hand side of that I shape where biology and mathematics overlap. Next, I move to physics and mathematics. There were 10 students who took physics and mathematics. Remember, there are already 5 we've included in the center, that purple 5. I subtract that 5, and that leaves me with 5. And the 5 goes in the left-hand side of the I, where physics and math overlap. Finally, I'm going to look at 1 subject at a time. There were 48 students who took mathematics. As I look in the mathematics loop, there's already a 5, and a 3. 5 plus 5 plus 3 is 13. So I already have 13 students in that loop. 48 minus 13 is 35. This is the number of students who took only mathematics. There were 45 students who took biology. Look at the biology loop. There's already a 1, a 5, and a 3 in that biology loop. 1 plus 5 plus 3 is 9. Subtract 9 from 45, and that tells me there were 36 students who took only biology. Then I moved to physics. There were 25 students who took physics. How many students are already in that physics loop? Well, 1 plus 1 plus 5 is 11. 25 minus 11 is 14 students who took only physics. Whew, I'm not quite finished yet. I've got 1 more piece to fill in. That's the number of students that are out in the universe and not in any of these loops. To do that, I'm going to add the numbers that I already have listed on my screen. When I add all of the numbers from all the loops together, I get 99. Now remember, there were 110 total college freshmen. Minus the 99 I already have in the loop leaves me with 11 out in the universe. So I've done all this work, and it's easy for me to lose track of what the question asked. So let's go back to what the question was. How many students did not take any of the 3 subjects? Well, that's that 11 that we just found. There were 11 students out in the universe, but not in any of the loops. This brings us to our next topic, Cartesian products. So one way to produce a new set is to take elements from 2 different sets and put them together as what we call a Cartesian product. Now, the way that we put these pairs together is specific, and order is extremely important for our Cartesian products. So let's suppose a person has 3 pairs of pants, blue, white, and green. Now notice I use capital letters for the pants. And let's suppose that a person has 2 shirts, blue and green. We'll call this set S. And notice that I use lowercase letters for the shirts. This will help me later distinguish between the pants and the shirts when I list the colors. Well, there are 3 elements in P and 2 elements in S. 3 times 2 is 6 possible ways or possible combinations that a person can put a pair of pants and a shirt together. We're asked next to draw a diagram that shows all the different possible combinations. Now remember, there are 6 possible combinations. I'm going to list the pants down the left-hand side. Then I'll list the shirts across the top. I have 6 empty spots in this table, and these 6 empty spots are my 6 ordered pairs or my 6 possible combination of a pants and a shirt. So I might have blue pants and a blue shirt, blue pants and a green shirt, green pants and a blue shirt, green pants and a green shirt, white pants and a blue shirt, and finally white pants and a green shirt. You can see our 6 ordered pairs. The pants-shirts combination are elements of all the possible pairs in which our first member of the pair is from set P, or the pants, and the second member is from set S, or the shirts. Now, because our first component represents the pants and the second component represents the shirts, our order is extremely important. So if we have green, blue, that represents green pants and a blue shirt. But if the blue comes first, remember that first component is the pants, this would be blue pants and a green shirt. These are 2 totally different outfits. Because our order is important in each pair, the pairs are often referred to as ordered pairs. Our ordered pairs are only going to be equal if the first components are equal and then the second components are also equal. A set consisting of ordered pairs is an example of a Cartesian product. So a Cartesian product is written as A cross B, is the set of all ordered pairs such that X, that first component in the ordered pair, comes from set A, and Y, that second component of the ordered pair, comes from set B. This is commonly read as A cross B, but it should never be read as A times B. So let's start listing some Cartesian products of some sets. Suppose set A consists of the elements A, B, and C. And set B consists of the elements 1, 2, and 3. In part A, we're asked to find A cross B. Well, there are 3 elements in A, times 3 elements in B for a total of 9 pairs that we're going to list. Well, I might pair A with 1. That's my first ordered pair. Or maybe I decide to pair A with 2. Or I could pair A with 3. Now, I don't have to start with A. I could start with B. And I could pair B with 1, B with 2, and B with 3. Then I could do the same thing. C is paired with 1, C paired with 2, and C paired with 3. For a total of 9 pairs. Part B asks us to find B cross A. Now notice the B is first here, so the 1, the 2, or the 3, the numbers are going to come first in each ordered pair. Again, there are 3 elements in B times 3 elements in A for a total of 9 pairs. We're starting with B, remember? So my first pair would be 1, A, then I'd have 1, B, and 1, C. Maybe I choose to start with 2, so I could have 2 with A, 2 paired with B, or 2 paired with C. Last, I could pair 3 with A, 3 with B, and 3 with C. And again, I have 9 total pairs. Our last example is part C. We have A cross A. There are 3 elements in A times 3 elements in A for a total of 9 pairs. So I start and I've got A, B, and C are my elements in A. I pair A with A with B, and A with C. Then I'm going to begin with B. So B with A, B with B, and B with C. Or I could pair element C with A, C with B, and C with A. And that's the end of our lesson for section 2.3.